Smith, and I'll be speaking about private algorithms with minimal space, counting distinct elements differentially privately. This is joint work with Shuang Song and Amardeep Guhathakurta, both of whom are at Google Research in Mountain View. So consider an algorithm that processes a data stream consisting of a sequence of records, D1, D2, etc. The algorithm processes these one at a time, and as it processes each one, it updates a relatively small memory. We'll call S the upper bound on the size of the memory. When it's done with the data stream, or when it's decided it's seen enough elements, the algorithm stops and produces an output we'll call A of D, which hopefully approximates some quantity, some function f of d that's of interest to the algorithm. So a typical goal for such an algorithm might be that for all data sets D with high probability, the output A of D lie within 1 plus or minus gamma of this target value f of d. And that the algorithm use small space. So let's say that the space bound S be bounded above by something polynomial in 1 over the relative error gamma, maybe the log of the size of the data stream, maybe some other problem-specific parameters. Okay. The question we want to understand is what is leaked by the output of such algorithms? And specifically, when can we limit what these algorithms leak without increasing significantly increasing the error or the amount of space that they use? Okay. We'll measure leakage in this talk using differential privacy. Given non-negative parameters, epsilon and delta, a randomized algorithm A is said to be epsilon delta differentially private. If for any pair of data sets, D and D prime, that differ in one record, the distributions induced by the algorithm on input D and the distribution induced by the algorithm on input D prime are approximately the same. Okay, specifically, for all sets of possible outcomes, we'll ask that the probability of the output lying in that set be similar to within a multiplicative slack of e to the epsilon, so think about 1 plus epsilon, and an additive slack of delta. When epsilon is less than 1 and delta is sufficiently small, this guarantee implies that the algorithm A reveals essentially the same information about any given individual Alice, whether or not her data were actually used in the computation. So essentially that it's revealing nothing about the Alice's record in the data set. Okay, and this is a strong guarantee. It avoids a lot of common attacks in data privacy. And it also allows us to reason about things like how different algorithms, the leakage of different algorithms behaves when we start composing copies of the algorithm. It's a definition that appeared in a paper of Dwork, McSherry, Nassim, and myself in 2006. Okay, so the drawback of the strong guarantee of differential privacy is that for essentially all interesting functions, differentially private algorithms have to make mistakes. They have to incur some error. And that's simply because there are lots of places, lots of neighboring data sets where D and D prime, where the function value typically will differ, and then the algorithm can't be perfect on both D and D prime. There are various ways of getting a handle on how much error is introduced and bounding it above. One way is the global sensitivity. So this is the maximum over, the global sensitivity of function f is the maximum over neighboring data sets, D and D prime. So these are data sets that differ in one record, of the difference between f of d and f of d prime. So it's been known since the original paper that there's a differentially private algorithm for any function f that approximates that function to additive error, the global sensitivity of f over epsilon. And the way it works is by computing f exactly, and then adding Laplace noise on the order of this global sensitivity over epsilon. So what we conjecture is sort of essentially the working conjecture for this paper is a more general version of that. Namely that for every function that has a low space approximation, so it can be approximated to relative error gamma with space S, and has bounded global sensitivity, then that there's a differentially private version that has the same space, uses the same amount of space, has the same relative error guarantee, but incurs just a small additional additive error of about the global sensitivity over epsilon. This conjecture may, of course, be too general to be true. I'm not sure. What we do in this work is try to see how it plays out for a specific function. So we look at counting distinct elements, or sometimes called cardinality estimation. So here the function of interest is the number of distinct values or records in the data stream D. This might, for example, represent the number of unique users in an ad campaign or the number of unique visitors to a website. If we care about space but not about privacy, there's a well-studied, this is a well-studied problem. One classic algorithm is the Flageolet and Martin sketch, and which is due to Flageolet and Martin, but also has been refined over the years. It requires a total amount of space about log u over gamma squared, where here gamma is the relative error as before, and u is some a priori upper bound on the number of distinct elements. So maybe it's the length of the stream or the size of the data universe or something like that. Okay, so this is a very small amount of space. In fact, slightly tighter bounds are known. I'll mention those later. On the other hand, if we don't care about space and we do care about privacy, as I said, the Laplace mechanism allows us to get additive error about 1 over epsilon, and that's actually optimal. We know that. And so what we do in this work is we give a differentially private algorithm that has space about, it has exactly the same space usage as the original Flageolet and Martin sketch, and additive error about 1 over epsilon. Okay, so it sort of gets us the best of both worlds. It assumes the existence of essentially an ideal hash function of some sort that could be implemented using, for example, a cryptographic hash. And I won't have time to talk a lot about the details, but that really doesn't cost us a lot of extra space in the execution. Our result improves on the previously known approaches for differentially private cardinality estimation in low space, and I'll mention that towards the end of the talk. I'll compare to those towards the end of the talk. I do want to start by just giving you a sense of how the algorithm works. So our algorithm is sort of, in fact, not just based on the Flageolet and Martin sketch. It, in fact, is the Flageolet and Martin sketch. So the thing we show is that the Flageolet and Martin sketch is differentially private essentially as is, with just a tiny modification, as long as there are enough distinct elements in the data stream. So differential privacy is a strong guarantee. It has to hold for all data sets. So the way we can sort of take this observation and use it is to basically just add some dummy elements, or what we call phantom elements, to the data stream in such a way that we guarantee that we always have the required minimum. And then what we do is we can adjust the final estimator accordingly by subtracting off from that estimate the number of phantom elements we added. This allows us to get a full differential privacy guarantee, along with a nearly minimal additive error and no increase in the space usage. Okay. Our analysis is based on this sort of this basic lemma that says the Flageolet-Martin sketch is differentially private as is. A very similar lemma appeared in this work, essentially concurrent work of Choi, Dockman-Solid, Kulkarni, and Yerahimовich that appeared at PETS just a few weeks ago. Although their use of it, the way they use the lemma is slightly different. Okay, so let me try and explain how, what's going on in this algorithm. So here's the basic, the Flageolet-Martin sketch has sort of a basic unit, which is then composed with itself to create a more complex final algorithm. To understand the basic unit, it's helpful to think of the hash function as mapping every possible record to an integer which is geometrically distributed when the hash function seed is chosen randomly. So instead of thinking the hash values as sort of binary strings, I'll think of essentially using that binary string to sample a geometrically distributed integer with parameter about gamma. So with that view of the hash function, the algorithm is very simple. I just pass over the entire data stream, I compute the hash of every element I see, and I just retain the largest value I've seen. And that's the thing I return as the output of this basic unit. Okay, so if there are k distinct elements in the data stream, then A is in fact, if there are k distinct elements in the data stream and the hash function is well behaved, then A is really the maximum of k independent geometric random variables. And that's a distribution we understand very well. On its own, it doesn't give us a great approximation to k. But if I run a bunch of copies in parallel and get various independent versions of A, then I can combine them to get a good approximation to K. And I need about 1/gamma² copies to do that. Okay, so that's the basic, that is the basic Fleschlein-Martin sketch. What can we say about privacy of that sketch? Well, we can analyze it using the following lemma, and I'm giving you kind of our version of this lemma. So given any epsilon greater than 0 and any distribution p on the real line, we'll consider sampling k+1 elements IID from p. And we'll construct two random variables, A, which is the maximum of k of these samples, and some lower bound b that we'll set in a second, and A prime, which is the maximum of k+1 of these, and this lower bound b. And what we show is that as long as k is at least 1/epsilon, and the lower bound b is set so that at most an epsilon fraction of the mass of p is larger than b, so the CDF of p at b is at least 1/-epsilon, then in fact, the distribution of A and the distribution of A prime are close in the sense needed for differential privacy. They're essentially epsilon close. Specifically, we get the multiplicative guarantee that we need for differential privacy. So this lemma is illustrated over on the right-hand side, where what we have are the distributions of the maximums of k and so k equals 10, so 10 and 11 copies of a geometric 1/3 random variable. And here the black bar is the value of b we would set for epsilon equals 1/5. And what you see is that most of the mass of the maximum is well to the right of that bar. Indeed, in general, we've sort of set the parameters such that the value of b, if we take it as small as we can, will not substantially affect the distribution of A and A prime, at least not enough to affect our final estimators. So what does this lemma really tell us about the Fleschlein-Martin sketch? Well, it says that the A and A prime here are the distributions of the sketch on neighboring data sets where the number of distinct elements is increased by 1. And so what this says is that the Fleschlein-Martin sketch is in fact differentially private as long as A, we have enough distinct elements. So if we add 1/epsilon, in this case, a sort of dummy or phantom elements to the data stream. And secondly, as long as we cap the value of A below by some, this quantity B. And as I said, B was chosen so it actually doesn't affect the final estimator. Okay, so that's the basic idea of the algorithm. I don't have time to go through the proof of the lemma. What it gives us is the following pair of results, namely there are differentially private algorithms with both of which have additive error close to 1/epsilon. Which one is better depends on the relationship between gamma and 1/delta. And they have the same space usage as the Fleschlein-Martin sketch. Update time 1/gamma². And as I said, the one downside is that we require this kind of strong ideal uniform hashing assumption to analyze differential privacy. And so that means in practice, they should be instantiated with cryptographic hash functions. They improve on previous work of this paper of Choi et al. From PETS this year that had higher additive error. Work of Pei and Stausholm also from this year, and an older work of Mir, Muthakrishnan, Nikolov, and Wright. And finally, I should mention that there's also a work of Kane, Nelson, and Woodruff that has a tighter, with no privacy guarantee, that has a tighter space guarantee, at least asymptotically. And we suspect our techniques actually apply to their sketch directly, but we haven't completely confirmed that so far. Okay, and so just the point I said before, but I want to emphasize is that this result matches the optimal error of 1 over epsilon up to this factor of square root of log 1 over delta. Okay, so we have some simulations. We look at data sets of cardinalities ranging from 2 to the 12 up to 2 to the 20. We set delta to be 100 times the actual cardinality of the data set in the experiment. So that's a range where the privacy guarantee is meaningful. We look at mean relative error as our main measure of accuracy. And then we look at 3 different ways of combining these parallel independent copies to get a final estimator. So on the top row are the results for the private experiment, the non-private experiment, I'm sorry, for the 3 different estimators. On the bottom row is the private version. And the main thing to take away here is that roughly they get very similar results. There are some interesting artifacts though. So at large values of M, so this is the number of, M here is the number of independent copies of the algorithm we're running. At large values of M, a couple of the estimators see like significant distortion of the estimate in the small, in the range of, the small cardinality range. And that's something we think could probably be fixed or debiased. But overall, the harmonic estimator generally performs the best, so that's the right-hand picture. With privacy, as I said, as we increase M, as we go from the blue to the green to the orange curves, we do see some trade-off as we see a big increase in bias at small sample size, small cardinality sizes. Yeah, so something we're working on is trying to improve that performance and get a more uniform bound. So overall, this work, we've looked at space-efficient cardinality estimation for optimal additive error with optimal additive error. That said, there's still lots left to be understood at the intersection of privacy and stream processing. And I think it's an interesting area that we'll see more work on and that is promising for future work. So thank you very much. And a preprint of our paper is on the way.